All right, welcome to section 2.3. This is the lecture video for integration by parts in the textbook. Our goals today in this lecture will be to first learn the integration by parts formula. We'll warm up to that at the start, and then mainly to use this to find more difficult antiderivatives, more difficult indefinite integrals, and then related to that, the definite integral problems than what you're used to in Calc 1. So for many of you, probably most of you, this will be a new technique for integration. Along the way, we'll actually review a couple things with derivatives and integrals that we'll need for these problems. Second, mostly the difficulty with the integration by parts formula is choosing the appropriate ways of decomposing our different expressions. And you don't know what that means yet, but you'll see shortly that it can be a difficult formula to use, even if it's something you have in front of you, there are choices to make. And finally, one of the biggest things in calculus in general is knowing what technique or what formula to apply when, and this will be part of the story today will be a nice mnemonic that you can take with you and use to decide not just when to use the integration by parts formula, but also in which order and how to write the decompositions. So to get started, to motivate this a little bit, I want to recall one of our main techniques from Calc 1 for computing any integrals, which was the U substitution technique. And typically this applied when we had a certain type of product of two functions, namely when that product of two functions, such as in this example, x times e to the x squared, actually is the result of taking a chain rule derivative, or really this is the result of a function times the derivative of the inside function. This is what we call U substitution, but the way we originally derived it in Calc 1 was undoing or unraveling the chain rule. So I'm not going to write out the general description, the general derivation of this U substitution rule, but it's probably something you're familiar with. And let's do this one together. So if we have the integral from 0 to 3 of x times e to the x squared dx, it might have been a while since you've done these U substitution integrals, so I'll help you through this one. Although if you want to try it on your own, feel free to pause the video and do it yourself now. X times e to the x squared, well, we see that there's a function in the exponent. That's we're thinking that as our inside function. I'm going to let that expression be u. That's x squared. And part of the technique, part of doing the U substitution is actually substituting directly into the integral any expressions with x's and trying to get everything in terms of u. In this case, the procedure tells us to make that happen, we should try to find du, which is take the derivative. That's 2x. Don't forget our dx. And I find it helpful personally to actually take this du expression and solve it for dx by multiplying or dividing some stuff to the other side. This will help with our substitutions. This is just a personal preference, but I encourage you to do this if it makes sense. So dx in this case is 1 over 2x times du. And what we're going to do now is take this whole expression here that we started with and replace everything in it that shows up in our table to the right with the appropriate expression in terms of u. I'm going to leave the integral bounds off, but it's important to remember when we have a definite integral, we need to do something to change those bounds. I don't have anything on the right that's just an x alone, so let's leave x, but just trust me on this. We'll be able to replace it in a moment. E to the x squared, well, x squared was our starting place. That's our expression for u. And then the reason I solved for dx on the right is I see there's a dx in the integral. There always is at the end. So let's just take this whole expression and plop it in there. 1 over 2 times x times dx. And the nice thing now, really my reason for doing this is I don't have to worry about trying to cancel in my mind. I can just visually cancel out the x's. And in a moment, sorry, that's my fault, that's the du. In a moment, we'll see that, and you can just stare at it, the x's are gone, everything is in terms of u, so we'll rearrange in just a sec. I want to handle these definite integral bounds. If in the original integral, with the variable x, if x equals 0, then u is 0 squared, that's still 0. But if x is 3, then u, which is x squared, becomes 9. So now I don't have to go back and change back into a dx integral or some x expression and solve from 0 to 3. We can just do this in one fell swoop. The other way to do this is solve the indefinite integral problem first, convert back to x, and then plug in 0 and 3 and subtract. But I'm going to do it this way because I like this better. So now let me pull out a 1/2, that's a constant. We'll integrate from 0 to 9 in the variable u, and the expression that's left is e to the u du. Hopefully this is an integral you should recognize, and at various stages in this lecture, I'm going to ask you, I'm going to ask you to ask yourself, do I know how to solve this integral? And if yes, then proceed to finish the problem. And if no, maybe you're missing something, you haven't remembered a property we learned in Calc 1, and then go check the table of integrals you have somewhere in your old notes. Or we need to do another technique or take another step. So there will be various places where we have to make a choice. Here, I know the integral of e to the u du is just e to the u. And so that just pops out the other end, and I'm doing a definite integral from 0 to 9. So in the end, we get 1/2 e to the 9 minus e to the 0 is 1. So that's our final answer. So if you pause and try this on your own, here's the answer. Compare it to what you got. Hopefully you got the same thing. Otherwise, take some time to read this through and practice more. Use subs on your own. These are good techniques to know. So you can see the next example will be a few slides later, but I'm going to switch back to the slides so we can build up to that point. All right. So the main idea here is when we have something in the right format, namely some expression, a function inside of a function, e to the x squared, and then the derivative of the inside expression also shows up multiplied by that, then we can unravel the chain rule. But this is, why should we expect every integral we're thrown to have this form? It's certainly not true, and we'll see some in this lecture video that you just can't do good old u substitution to. So what do we do? Well, we have some other, luckily we have some other integral rules that we can, or rather differential rules we can unravel, just like the u substitution rule is really doing the chain rule backwards. We also have a product rule for differentiation, and we definitely don't have a product rule for integration. It's important to remember that the integral of the product of two functions is not the same as the product of their integrals, and that last example was already an example of this. However, the product rule says that if I have two functions f and g, and I want to take the derivative of their product, then in some sense we have the output of this can be written in terms of f and g again, as sort of an entangled derivative product. So the way that I like to remember this rule is we take the derivative one at a time and add up the results. This actually works for products of more than just two functions, by the way. If you've never seen this before, you can try with f, g, and h, 3 different functions. Apply the product rule step by step, and you'll get out 3 expressions added up with 1 derivative in each of the expressions. So this is a handy way to remember the product rule. However, this doesn't tell us anything about integrals until you remember that if the derivative of f times g is equal to this expression on the right, then the automatic integral rule that we get for that is that this expression inside the brackets on the left is equal to the integral of the expression on the right plus c, or rather it's one of the antiderivatives. So if something's derivative is this stuff on the right, then the integral or an integral of the stuff on the right is the stuff inside of the brackets on the left. Let's put that to work in this example. I didn't mean to go ahead. If we want to compute the integral, the indefinite integrals, we want to find some antiderivative of x squared cosine x plus 2x sine x dx. Think about it for a moment. Maybe pause the video and see if you can figure out, using this large hint here with the product rule, what an antiderivative of this expression is. And at the end, I'm going to ask, once we work it out together, how to check your work once you've figured out what the integral is here. How can you check that your answer is right? So I'm going to switch over, and let's do this one again together. Okay, so we have an expression, and actually at the bottom of the screen, you can see a reminder of the chain rule. So what I really need is some function f and some function g, so that the two terms here, again, look, the right side of the chain rule, or sorry, the product rule is supposed to be the thing we stick into the integral, and then the thing we're taking the derivative of in the product rule is supposed to be the output of the integral procedure. Remember that integrals and derivatives undo or cancel each other out. So if this whole expression is supposed to be the sum of f and g stuff multiplied with one derivative taken at a time. Can you see which function we can choose as f and which as g? So pause if you want to think about this for some more, but I see that in the first expression versus the second expression, there's an x squared and a 2x. So it looks like one of those is the original function and the other is the derivative. Let's see, the original function x squared, I'm going to make that my g of x. And immediately I'm just going to record its derivative. And that leaves f of x to be the other function. Well, if g of x is x squared, the other piece needs to be the derivative. So f of x could be either sine or cosine. But I need something to be, f or g prime in the first expression. That will be, cosine is going to be the derivative. So that came from taking the derivative of sine. If that was confusing, then think about this on your own and see if you can see not just that I chose the right functions, we'll work it out in a moment, but why I made those determinations, and see if you can come up with that on your own again, just thinking it through. So let's take this integral expression. The problem says to compute this. So let's compute it. It's supposed to be equal to, well, I'm going to write it as f prime x times g of x plus, well, it doesn't really matter if I write it in the wrong order, but oh yeah, sorry, g prime x f of x dx. This is supposed to be equal to the expression f times g, again, because the derivative of this by the product rule is equal to the integrand. And f and g I just wrote down carefully, so it's easy to just copy paste these in now. So f is sine of x, g is x squared, and then I'm taking an indefinite integral, so I want a plus c. Just kind of personal preference, I like putting algebraic expressions like x squared before trig expressions like sine x. So I'm going to leave this as my final answer. This is also a valid expression if you wanted. There we go. That's our first use of the backwards product rule. Let's give this a name, the backwards product rule. And it sort of seems even more complicated than the complicated version of u substitution I gave you on the first slide, but it's not so bad. So let's try to work this out. How can we make this formula more useful than always having to write down an f and a g and then kind of carefully examining if we made the right choices? So actually, let me go right back to the slide, or rather the tablet. And let's kind of sketch some thoughts out about this. Oh, you'll see an example below. I'm going to try to cover up the formula. So one nice thing about u substitution is we could have written it as, this is not going to be related to this question, but we could have written, g of f of x, take its derivative, and that's, g prime of f of x times f prime. This is what the chain rule says. Kind of the ordinary chain rule for derivatives. We could have turned this into an integral formula with a bunch of g's and f's around, and it would have been gross. What's nice about u substitution is it just replaces a lot of the complexity of that potential formula with a new variable or a new symbol u. I'm going to take the same approach here. So if I I'm just going to start picking things and seeing what happens. So if I take the expression f of x, which could be some big expression in terms of x, I'm going to replace that just with the letter u. I'm also going to replace g with something, but I can't use u again. So I'm going to use a new letter v because it's the next one in the alphabet. And let's just see what du and dv are. If we were to take the derivatives of these expressions, see what shows up. Well, if I take the derivative of u, that's f of x. So I'll get f prime of x, and I'm going to leave a dx in there, and it'll become clear in a moment when we write down the full formula why I did that. Likewise, dv, that can be expressed as g prime x times dx. Another way to think about this is if I didn't write that dx there, f prime of x, another way to write that is the derivative of u with respect to x, since u is f of x. So I'm gonna write it this way though. Okay, so how can we rewrite the formula that we have? This is f times g is u times v. We're taking its derivative. I'll write the derivative version first. Let's see, f prime of x times g. That's du times g is v. So I'm actually going to switch the order here and write it. The derivative piece is going to go second. So g is v du. And then it's just the opposite for the other one. So f is u and g is, g prime is dv. Now you might get annoyed that I'm dropping some dx's, but let's make it actually look like something with dx's when we take the integral. So if we take the integral of a derivative on the left side, they remove themselves. So uv is equal to, now we're going to take an integral of the whole expression, v du plus the integral of u dv. Let me make that a little cleaner so you can see it's a u and a v. So the product of two functions, u and v, which are secretly f and g, functions of x, is equal to the integral of v du plus the integral of u dv. Now in practice, u and v are written in terms of x, and so are their differentials du and dv. So we plug a whole bunch of stuff in here, and you'd actually see two integrals pop out. How is that useful? Well, in this form, this looks even more complicated, or maybe it looks as complicated as we had it before. So how is this going to help us? Well, let's suppose that we can stare at some integral problem, and there's actually one right at the bottom of the screen right now that we'll work on in a moment. And suppose we can sort of, peer into the mist and see, oh, look, this is actually of the form integral of u dv for some functions u and v. Let's pull that out to the left side. Well, if that's true, then this key expression, this really reinterpretation of the product rule in terms of integrals, reads the integral of u dv is equal to uv minus the integral of v du. And you might have one more objection. Look, we just took an integral u dv and replaced it with something. Okay, great, uv is some function minus another integral. Well, what the hell? We're supposed to be solving integrals here. Well, the whole point of this technique, and we're going to practice this for the rest of the video, is in many instances, the new integral on the right side, notice it's different than the one on the left, will be easier, will be solvable, or at least will be closer to something you can solve. And you might have to use some other techniques along the way. So that's what we're going to be doing. And let's start talking about it. This has a name. It's called the integration by parts formula, and this was the formula mentioned on the first slide. Here's a formal statement just so you can have it all in one place on this slide, but it's what we just derived together. So let's suppose we have an integral with some functions of x in that, gross looking integral, but we can, kind of read the source code and see that, no, this is really of the form the integral of u times dv, where u and v are two different functions of x. U is some function, that was our f of x above, and dv is really the expression v prime of x dx, or for us it was g prime of x dx. So if we can find an integral of this form, then the following formula will help you evaluate the integral. The integral of u dv is equal to uv minus the integral of v du. I don't have a good way of memorizing this. I just usually remember the integral of u dv equals uv, and then I just know something swaps. So there's a minus sign that you're going to have to remember. You're going to have this formula down at some point. And then inside of the new integral, if you don't remember what happens, just look at the first thing you started with, u dv, and swap the roles. Now it's v du. That's the best I can do for how to memorize this. Here's an example. Let's jump right in and use our new formula. If you want to try this on your own, this is a good moment to pause and write this down and choose a u and a dv. Remember that our first formula, the first expression in the formula is the integral of u times dv. So we don't get to choose u and v by looking at this integral. We choose u and dv, which is sort of weird. But try to give it a shot before I work it out with you, and then check back in once you've made an attempt. Even if you don't get all the way through, that's okay. So u times dv. Well, just looking at this, I see there's an x and then there's an e to the x dx. So if I didn't have any good idea how this works, I might just try to replace the first thing I see with a u. I'm going to set u equal to the x. And notice in the integration by parts formula, before we do anything with the exponential, there's a du that shows up. So I need u and du to write out the whole formula. Remember that du is, well, the derivative of x is 1, but I need my dx to hang around as well. The nice thing is once you choose u in integration by parts, the entire rest of the expression has to be dv. So u times dv is x times whatever's left. I'm going to write it down here in the bottom right, and then we'll have to really deduce what v is from this. This is the tricky part sometimes. So e to the x dx is our dv expression. Now we have to ask ourselves, we had some function v, and we took the derivative and got dv. What did we start with? Well, the derivative of e to the x is e to the x. So you can sort of just eyeball it in this case. And in general, you might have to take a separate antiderivative to figure out what v is. This is what makes these integration by parts a little longer and more complicated than what we've seen before. But now we have our choices of u and dv, and we automatically get a du and a v. Let's write out the entire formula using our choices. The integral of x e to the x dx is equal to, sorry, I wrote an integral, but I really should write u times v. U is x, v is e to the x. I'm just reading off my table in the top right, minus a new integral, which we'll have to deal with, of v times du. Well, v is just e to the x, and then du, luckily, reduced in complexity. This is sort of the name of the game with integration by parts. The new integral on the right side is something we can solve. Remember, a couple minutes ago, I said, I'm going to ask you to ask yourself a few times throughout the video, do I know how to solve this integral? So every time you perform the integration by parts formula, kind of do the dance in one step, you will get a new integral on the right side. It's part of the formula. And you should ask yourself, do I know how to solve this one? Did my life get any easier after one step? And if so, do it, and you're almost done with the problem. Now, actually, at this point, you can probably finish the problem faster than I'll finish talking about it. So I encourage you to do that, or pause and take your time and do it. And if you don't know how to solve the integral, then again, go check your tables in case you're forgetting one, or see if we can apply some other combination of techniques. Maybe we'll have to do a separate substitution or something like that. In this case, I know what the integral evaluates to. I'm going to copy paste my uv expression. That's already in there. The integral of e to the x dx, and we actually secretly did that up here to find v, is just e to the x. And now I've removed all of my indefinite integral symbols, so I'm just going to throw in a plus c. So we can read this back as the indefinite integral of x e to the x dx is equal to this whole expression, x e to the x minus e to the x plus c, full stop. So I want you to pause and think about this question. How would you check your answer? How do you know that this is the correct indefinite integral? Or rather, how do you know that this is an antiderivative of the integrand that we started with? We'll do some more examples of this together, but let's keep talking through our observations. Okay, well, here's one interesting question. I actually don't want to finish with this problem quite yet. We made a choice and we said, let's let u equals x, and then the rest had to be dv, that was e to the x dx. What would happen if we swapped the roles? What would happen if we jumped right in and said, oh, look, e to the x, I know how to take its derivative, it's just still e to the x. Let's go back and just see what happens. So you can see on the slide here, the choices of u and dv if you made that initial decision of, I'll copy them here again, u equals e to the x instead, and then dv is everything left, that's x dx. What would happen? Well, in order to write the integration by parts formula, maybe you want to pause here again and try it out for yourself. I need to write down du and v. So just reading from this, the two choices I made for u and dv. Du is, well, derivative is e to the x, and then I'll throw in a dx. If dv is x dx, I had to take the derivatives of some v expression whose derivative is x. Well, I know it's, by the power rule, it has to be something x squared. And to get a 1 times dx, I need to cancel out my 2 somehow. I'm doing this a little bit quickly, maybe, for some people's liking. You can perform a separate indefinite integral calculation. You're really taking the integral of dv to find v. You can do that in the margin or on a separate piece of paper if you like. Or if you take a guess, I kind of like this approach. I know it's something like x squared. take a guess and then take a derivative of v just to double check you get x dx. In any case, we have our u, v, du, and dv. Let's go feed them into the formula. So the integral of x e to the x dx is equal to u times v. That's I'm gonna sort things a little differently, but u times v is 1/2 x squared e to the x. Notice I wrote those backwards, but you're allowed to multiply in both orders. Times the integral of v du. Let's see, v is 1/2 x squared, and du is e to the x dx. And now is where I want to pause, and we should say, well, we've got this part. Did our life get any easier? Do we know how to integrate? Pull the 1/2 out, get it out of the way. Do we know how to integrate x squared e to the x dx? I don't. And if you have an idea, let me know, and maybe we can solve this problem a different way. But off the top of my head, I don't know how to solve that integral. You can try a u substitution and try to get your way around this difficult looking expression, but I don't think you're going to get very far. And ultimately, if we stare at the thing and we can't do anything with that expression, then it probably means we made kind of an unfortunate choice of u and dv. I won't say the wrong choice. This is still certainly a valid equation because it follows from the formula. It just means that we can't completely solve the integral because we're stuck with a different integral that we don't know. So if you accidentally did it this way when I said pause and trying to solve in the previous problem, that's okay. It just means you learned something new. Don't choose u equals e to the x if you have x times e to the x. Now, hopefully this will give you ideas for other problems. We're going to formalize this in the next step. So let's talk about that now. And this is the trickiest part for many people. For me as well, this is the trickiest part of integration by parts. What function do we choose for u, which we'll have to take a derivative of to find du? And maybe more intimidating is, what do we choose for dv? And that's the thing we'll have to compute an integral of to find the original v. We'll have to go backwards from that. The key observation, and this is not a rule, this is really just a set of guidelines or helpful hints for integration by parts. But the key observation is that taking a derivative most of the time makes a function simpler. Think about the power rule. It reduces the exponent in any polynomial expression. Think about ln of x. It spits out a 1/x when you take the derivative. And yeah, okay, that has a denominator, but it's simpler than ln of x because I can't tell you any values of ln unless I plug in e or something. So it makes functions simpler for the most part, not always. Many times, if it doesn't make them simpler, it doesn't make them more complicated. Think about e to the x. Taking its derivative just leaves e to the x. Trig functions have other trig functions usually as their derivatives, so things don't get too much more complicated. On the other hand, integrating tends to make things more complicated. So what we want to do, and the chart below gives us a way of organizing these thoughts, is we want to pick u so that du gets simpler, and then in the expression v du on the right side of the formula, we'll have a simpler integral to solve. And after centuries of carefully muddling over this problem, mathematicians came up with the following acronym, ILATE. I usually just remember it as late until I need the I, but ILATE is a mnemonic that will remind you what's the best choice of u versus the best choice of dv. So the acronym from left to right gives you good choices of u at the start and bad choices of u, or conversely, better choices for dv at the end. So I'll just read through ILATE and explain each one. The I is inverse functions. If you see an inverse function, like we'll see a tan inverse or arctan in a moment, or something similar, choose that for I. Otherwise, skip and just remember late. It's kind of the one that I ignore until it's very obviously in the problem. But if it's there, use that as u. Then you have to know your derivatives of inverse functions. So that could be some review to look at. But let's go through the main late. L is for logarithms. Anything with a log, a natural log, I mean, is a good choice for u, because when we take the derivative, it often gets simple and gets rid of that ln expression. Next, the A stands for algebraic, which for us really means polynomials. There's a typo here, but algebraic means polynomial expressions, such as our x in the previous problem. X was a good choice for you because, well, there's no logarithm, there's no inverse function, and algebraic is the next letter in late. So, that's what we did. But also it was the one that worked. And if we had chosen exponential, which shows up later in the list as our u, we saw on the last slide that this failed in this example. T is for trig functions, and finally E is for exponential functions. So you'll see in both of the problems we've worked through together, we actually used the late method or the ILate method without saying so, and we ended up with the right answer. And in the last step on this slide, when we flip things around, we actually were not able to solve the problem. So this is one of those trust the method if you want to think about why this works. There's a bit of technical integration technique and really staring at your tables of integrals for why this is a good guide. I want to remind you, really want to warn you that this is not a rule or a theorem or a procedure that always works. It's just a general set of guidelines for how to choose your u and dv. For every rule like this, there is always a handful of integrals that calc professors know that can trip up students. So be on the lookout for those. Even if I don't give them to you, they're all over the internet for sure. Just to practice, let's make a choice for u and dv in each of the following integral expressions. If you want to try it on your own using ILate for each of these three expressions, just write down u, and then the rest of the integrand has to be dv, and compare to what I do in a moment. Just practice with ILate. I'm going to switch over and do this for each of these three expressions. Oops. Don't look at the green stuff below yet. So let's apply the acronym to the following products. Remember that I'm going to start from the left, and the first thing on the list that I hit, I'm going to choose that for u. So with x to the fifth ln of x, I don't have any inverse functions. L is for log. Oh, look, I have a log function. So I'm going to choose u as ln of x. And let's just write down dv. Automatically, everything else under the integral has to be dv. So that's x to the fifth dx. And this gives us a starting point for writing down an integration by parts formula. But let's go on to the next one just to practice with ILate. I don't have any inverse or log functions. I do have an algebraic expression. Remember, algebraic means polynomials. So x here is algebraic. Let's choose u equals x, and dv equals sine x dx. And finally, in the last one, okay, you see there's an inverse function. That's a dead giveaway. That's what the I is for in ILate. U is tan inverse, and dv is x squared dx. It's everything left over. Sometimes tan inverse is written arctan, if that's more familiar. I don't have a preference. You can pick either one. Just stay consistent in each problem when you use that notation. Okay, cool. So the rest of this question, I'm going to leave to you. Try to write down the integration by parts formula for 1, 2, and 3. And then once you're able to do that, in order to do that, you need to find du and v for each of those three problems. Once you've done that, try to work out the integration by parts formula and integrate the new integral v du on the right side. So you can pause and do it now. You can do it as an exercise at the end. Either way, let's press on and talk about a couple more situations that can happen. So sometimes you might have already seen this coming. If we perform integration by parts, we might get a new integral expression, such as, well, it'll always be the integral of v du in our formula, but we saw a couple examples of this, like in the e to the x problem a couple slides ago. And it might not be an integral that you recognize. Sometimes that's the end, that you're out of luck. You just chose the wrong u and dv, and you can go back and switch things around and try it again. Sometimes it might have not been the end of the road so soon, and you can actually perform integration by parts again on the new integral. I'll show you how to do it in this problem. And the dead giveaway for this type of problem is when the complexity of the first integral was reduced performing integration by parts. I'll point it out when we do the whole procedure in a moment, but the dead giveaway is when you're looking at the new integral, did it get easier even if you don't know how to solve it yet? By complexity, I mean, the size of the exponent. If x squared drops to just x in this case, if you removed an exponential or a log or something nasty or an inverse function like that, that's an example of reducing in complexity. So let's go do it. Whoops. Okay, there we are. This is a good time to pause and use ILATE to make a choice of u and dv. I've set up the table here for us already, and then compute du and v and write out the integration by parts formula. Actually, I want everyone to do this right now. Whether or not you've been pausing and trying other things as an exercise, this is the one I want you to do. So pause the video now, choose u and dv, compute the rest of the table that I drew for you, and then just write down the first step, which is the formula for integration by parts. I'm going to fill this out now. So using ILATE, I have a trig and an algebraic, so I'll choose a algebraic as my u, that's x squared. And that means dv down here is everything left, cosine of x dx. Let's go out of order and do v first, just for fun. So if dv is cosine x dx, we had to take the derivative of something to get cosine, and I know that the derivative of sine of x is cosine of x dx. So that's a good choice for v, or rather that is the v that we need. On the other hand, okay, we have u is x squared, du then is going to be 2x dx. Remember in the u substitution problem that I substituted my integral bounds for the u expressions as well. I recommend against that in an integration by parts problem. Instead, I'm going to take the indefinite integral first and just completely solve this indefinite integral problem to get some collection of antiderivatives, and then I'll choose one of them. I'll drop off the plus c at the end and then plug in the bounds 0 and pi and subtract. So this is a different way than I did at least for integration, for substitution, but this is a strong recommendation to do things this way. Okay, so we've got our setup. This is of the form integral of u times dv. You can see in the table. So the output of the integration by parts formula will be uv, that's x squared sine x, minus the integral of v du, that's going to be sine x times 2x dx. So I'll have 2x sine x dx. And here's where you want to pause. Now, pause the video, sure, but when I'm solving these problems, I really just take a breath and say, do I know how to solve this integral? Well, this is of the form, you can pull the 2 out. We'll do that in a moment. This is of the form x times sine x. We started with x squared times cosine x. So the issue there is I have really 2 completely unrelated functions. I don't think I can do a substitution. There's no function inside of a function, and one is algebraic and one is trig. But luckily, the complexity decreased. So I went from x squared just to 2x. That's a lower power of x. And it stands to reason that if we did it in one more step, we'd drop the power to 0. That would just be, or really the derivative of 2x then would be 2, in which case we would completely get rid of the algebraic expression. If we do things carefully, we should just be left with a trig function to evaluate. And we know integrals of all of these different trig functions. So this is an example where doing integration by parts one more time and kind of sticking with the current strategy is advisable. If you wanted to go back and try a different choice for u, namely if you took u equals cosine x dx, give it a shot if you're curious. I don't think it's going to give us any simpler integral to solve, so let's proceed with this. So my best advice now is to kind of put a box or somehow indicate we're just going to deal with this new integral for a moment. I'm not going to write down a table with u and v. And notice that I've already used up my variables u and v in the first step. And they're still on the page, so I don't want to confuse the reader. I'm going to choose new variables. And just because at some point you'll probably memorize this formula with u's and v's, I'm just going to put a bar over u. So u bar is going to be the new thing that I want to take the derivative of. And then we'll also need dv bar and v bar. But first, let's figure out u bar. So the thing I want to take a derivative of, using LATE, I have an algebraic and a trig expression, and a comes first, so I'm going to use 2x. And I could pull the 2 out and then just use x as u bar. It really doesn't matter. You'll get the same answer in the end. Du bar then is just 2 times dx. And that's going to be nice because in the new integral, after applying the formula again, we'll just have a 2 instead of 2 times some power of x. On the other hand, we need v bar. dv bar is everything but the 2x, so that's sine x dx. And whose derivative is sine of x? Well, it's something with cosine. So if I wrote down cosine, I want to double check by taking a derivative. But the derivative of cosine is negative sine, so actually I need a negative cosine for v bar to compensate. So now let's proceed. This is all kind of in the margin. If I had a little more space horizontally, I'd scoot this to the right even more. I'm going to take a drink of water, and if you want to perform integration by parts a separate time while I'm doing that, this is a good time to do it. Try it for yourself. I'll do it in a moment. So I'm going to copy down the first expression that we had, our original u times v. And now I'm going to subtract a new expression. We're going to replace this second integral on the right side, which is of the form the integral of u bar times dv bar, with its own integration by parts, which will be of the form u bar v bar minus the integral of v bar du bar. So let's plug everything in and see if we got anywhere with this. So u bar, that's 2x. V bar is negative cosine x, so I'll throw in a minus out front, cosine x. And now here's the key moment. Did we make the integral solvable? Well, v bar is negative cosine x, I'll make that a plus out front, times du bar, which is 2 dx. And we should stop and ask ourselves, did we come up with an integral we know how to solve? If we pull the 2 out, this is the integral of cosine x dx, and that's one that you should know. If you want to solve the problem, maybe you want to sketch it out while I'm kind of very carefully, thoroughly going through with you, see if you can beat me to the end. But in general, it's a good idea to go slow on these problems. Let's finish everything and write the complete answer. So again, I have a minus sign. I'm going to distribute here. I'll get a minus in front of the second integral again. This is 2 times the integral of cosine x dx. Cosine is the derivative of sine x. That means integral of cosine is sine. And here is the indefinite integral of the original expression, x squared cosine x dx. Remember that we need to integrate from 0 to pi. So we'll do that in a moment, but I want to pause here and ask a question. How would you check your answer? How would you check that this is the correct indefinite integral? If you want to think about this, and I'm not going to tell you how to do this, I hope this is something that we can talk about in class. But if you want to pause and do it now and just think about the problem, and once you have a way of verifying that this is the correct indefinite integral, then carry it out and double check we got the right thing. And if not, hold on to that question. We can talk about it later. For now, let's finish the problem. So we wanted to integrate from 0 to pi, and I have an antiderivative I can use with the fundamental theorem of calculus. So let's go throw that down here. I think I have enough room. Integrate from 0 to pi. Oh, let's see. Just to save some space, we know a lot of things are 0. A lot of trig expressions are 0 if I plug in 0 or pi. Let's think about the unit circle. So 0 and pi are both y values of 0 on the unit circle, and sine is the trig function out of cosine and sine. It picks up the y value. So anytime I plug in 0 or pi into sine, it's just going to give me a 0. So the first expression when I plug in a pi is 0. The next expression doesn't have a sign, so I'll get 2 pi times cosine of pi. Cosine of pi is the x value over there on the left, that's -1. And then there's another sign, so that's -0. And I need to plug in 0 and see what happens. First expression has an x. Second expression has an x. Last expression doesn't have an x, but it has a sign, so that's all 0. So ultimately I'll get -2 pi. This was a definite integral problem, not an area. So this is really the signed area of that function x squared cosine x from 0 to pi. And I encourage you to try to sketch this function using any sort of rough curve sketching you have at your disposal. Hopefully a technique you learned pretty well in Calc 1, or just go graph this with the graphing calculator or Wolfram Alpha and kind of do a gut check. Does the answer -2 pi look like it is reasonable for the signed area between this graph and the x-axis? All right, we've got a couple more things to talk about. We're almost done. So this is just a quick reminder. I'm not going to really dwell on this too much. Contrasting with U substitution, where in the case we did, we were able to completely eliminate the variable x from the integral expression, and with a definite integral that allowed us to replace the integral bounds with U bounds. With integration by parts, everything turns out in terms of x in the end, namely because U times V, it's two different variables, and we don't know how to integrate or do anything with two variables, but U times V is just expressions in terms of x. So everything needs to stay in terms of x, which means that a good approach for this is carefully solve an indefinite integral separately and then apply the definite integral bounds at the end, like we just did. There's a type of situation that can occur when you are applying the integration by parts formula once, and the new integral you get out doesn't reduce in complexity. In the previous example, our x squared became a 2x with one step, and that was easier to deal with. We only needed one more step to produce the final answer after that. In this problem, we'll see that sometimes our life is not that easy, but that's okay, because we should trust the system and try to apply integration by parts one more time. This is not a hard and fast rule. This is just a situation to be aware of. So I want everyone to pause again and write out one step of integration by parts. This is of the form integral of u dv. So I want you to use ilate to choose u and dv, and then carefully write out the right side of the formula. But stop after that. You'll see you'll get out a new integral of v du that you probably don't have any way to solve, given what we know so far. Let's do it. I'm going to use ilate to choose the following expressions, and I'm going to move a little quicker through the first part so we can get our expression, or our first formula. This is one part you might want to slow down. Finding v, I'm just going to tell you something that works, and you can verify my answer by taking a derivative. But if you didn't know how to get that, then carefully write down an integral. Maybe do a separate substitution. You might need to use a different variable than u, since we're already using u for something different here, and double check that you know how to get v. So let's take this expression. This is our integration by parts, and we should get u times v. It's going to be 1/2 e to the 2x cosine x minus the integral of v du 1/2 e to the 2x times du, that's going to be negative, we'll make that a positive, sine x dx. So what happened here? We can pull the 1/2 out if we want to get it out of the way, and we'll have e to the 2x times sine x in our new integral. And practically speaking, that's not any more or less complicated than e to the 2x cosine x. Sometimes I think of this as we just spun our wheels. So if you're in this situation, sometimes the following trick works. I can't promise it will always work, but I want to show you what happens if we just trust the system and go one more step into integration by parts. I'm going to bracket the integral that we're solving here. I'm going to use u bar and v bar like I did before. Using late, again, we should use the trig function as our u bar. It'll be sine x. That means du bar is cosine x dx. dv bar is whatever's left. That's 1/2 e to the 2x dx. If you want, you can pull the 1/2 out and you'll get a different v bar and dv bar. You'll have to distribute it at the end. And I'm not claiming that either way is better. I just happen to do it this way. So v bar then is something whose derivative is 1/2 e to the 2x. I'll give it to you again, and you want to carefully think through this if you're not sure why I got that. The hint is that you're using the chain rule on e to the 2x. And I did that up here as well. Okay, let's make this integration by parts formula replacement. So I have the same first expression, put some big brackets, and this second integral now is it's the integral of u bar dv bar. So it gets replaced by u bar sine of x times v bar, times v bar 1/4 e to the 2x minus the integral of v bar times du bar. Which I think I have everything correct here. And now you're probably yelling at your screen, why did you do that? Where did that nice green color go? Why did you do that? Because look, we started with the integral of e to the 2x cosine x. And look what we just got out, something with e to the 2x cosine x dx. That highlighting green doesn't look great. So let's just underline it. So I got out a new integral after 2 steps of integration by parts that contains the same integrand. It's off by 1/4, but it's the same integrand as we started with. Here's the magic. Sometimes I like to think of this as rounding the corner. We just need to get back to the place we started with new information along the way. So what's the new information? Well, if I expand the original integral, e to the 2x cosine x, using integration by parts twice, I see that that expression is equal to this expression. And the original integral shows up on the right side. And what's nifty is I can actually take this whole expression and move it to the left side of the equation. And I have one of these integrals here, and I have another 1/4 of these integrals here. So now I'm really going to take the 1/4 out. If I add those two things together on the left side of the equation, I really have 1 plus 1/4 of them, or 5/4 times the integral e to the 2x cosine x dx. Can you see how to solve the rest of the problem now? That's what I did. Said it in words, but I'm going to add this expression to both sides of the equation. Sorry, not d cosine x dx. Add it to both sides of the equation and then combine like terms on the left side. Can you see how to finish the problem now? Pause and see if you can write it out. I'm going to do it right now. So once I've added all of the integrals up on the left side, I'm left with 1/2 e to the 2x. I think I have a typo here. Should all be 2x cosine x plus 1/4 e to the 2x sine x on the right side. And there are no integrals left. So you know what? I've almost evaluated everything. Let's throw in a plus c since this is an indefinite integral problem. And now if you weren't sure how to write everything this way, now I've done it for you. How can we find the indefinite integral of the original green shaded piece at the top? Do you see how to do it? Pause and try to write it down. And I'm going to do it for you right now. The key piece is we want to find the expression here. And I just have a 5/4. So let's multiply by 4/5 to get rid of that. 4/5, kind of sneak it in there, put some big old parentheses. I don't need to multiply through by 4/5 times c because it's just some constant. So the original expression, the integral of e to the 2x cosine x dx equals 4/5 times 1/2 e to the 2x cosine x plus 1/4 e to the 2x sine x plus c. Okay, and that's it. This is the last problem we'll do together. Just like I asked in a couple of problems already, I want you to think about how you would check your answer once you get this expression. How do you know that this is the correct indefinite integral? And with that, let's switch back and do a bit of a recap and take stock of what we learned. This is a little bit complicated. I don't necessarily think about integration by parts with this full diagram in my mind all the time, but you know, for some people, this is a really good organizational tool, and maybe you might print this out or copy some version of this down for yourself. You should start here can you view this expression, the original integral, as, and it's something in terms of x to begin with, as an integral of the form integral of v du for some v and some du? And if so, let's proceed. If it's not of this form, by the way, you have to have some other technique to integrate it. There are other integrals out there that are not solvable by any of the methods we've learned so far. So this isn't strictly the end of the story. It might just be out of our reach for now. But if it's not, and we gave it to you on a quiz or an exam, you have to be able to solve it a different way, such as with a substitution. If it's of the right form, let's go and do our thing. Can you apply a use substitution? Oh, okay, well, yeah, do it. If so, if not, how does this compare to the original integrand? There's a typo here, by the way. If it's simpler, or at least similar in complexity and in form, trig times exponential, for example, try to apply integration by parts at least one more time and see how you did. See if you can get a little closer to a solvable integral. If it got more complicated, chances are you made the wrong choice of v and u and dv in the original step. You might want to go back a step and try something else. If it not only became similar, but became just a constant multiple. In the last example we solved was 1/4 times the original expression. Try to solve it by pushing all of the like terms together. You can think of that as an equation in that integral expression and solving for the integral expression. If you want to replace the integral with some letter like capital S for sum or capital I for integral, it'll make this equation solving a little easier. But that's it. Once you get here and apply integration by parts, if you need to do it multiple times, you're just going to go back to the start and assess that new integral separately from the rest of the problem. Here's some summary questions for you to think about. First, what type of integrands, the functions under an integral symbol, are good candidates for integration by parts? How is u, the symbol u in our integration by parts formula, handled differently than it is in u substitution, the other place we use the letter u? How is the acronym ILATE used in integration by parts? And finally, under what conditions would we want to apply integration by parts more than a single time? I'll leave those to you to think about. And here are 2 problems for you to do as exercises after the video is done. Which of the following in this table of integrals can be integrated using an ordinary use substitution? If you want extra practice, for those that you can solve using a substitution, perform the substitution in practice. For those that are not, if you want some extra practice with today's content, see if integration by parts makes sense and try to solve it that way. That gives you, looks like 16 different integrals to try to attempt. Some of these, I'll warn you, you can't do with either one, and you can try them, but there are at least 3 on the table that I see without thinking too hard that you cannot solve using any techniques you've learned so far. Here's another problem to think about. We can secretly think of the integral of ln of x dx as an integration by parts problem. And the huge hint that you probably won't think of until I show you this is that if you write ln of x as 1, a constant 1 times ln of x, you can actually apply integration by parts to this. So if you take this literally and try to just go through the method, viewing this as a function times another function under the integral, and you can't do a substitution on it, try using ILATE to get a start on the problem, and then perform integration by parts once you set up the formula to try to compute the antiderivative. If you've never seen this before, this will give you an expression, if you do this correctly, for the antiderivative, or rather the indefinite integral of ln of x dx. You can check your answer at the end, just as I've asked you to do in other problems. And now you know the integral of ln of x dx. So that's it. Thanks for tuning in. I will see you next time.